So we are here. Day 4, last day looks for, well, we have some AP practice questions again. I'll put some more of that. In fact, your homework tonight will be on the website. It's just, I think, like 6 multiple choice questions. All right. So, area of accumulation function. Step 1, the graph of f prime is given in the figure 6.1. Sketch the graph of f in the case which f is 0 equals 0 and f is 0 equals 1. So we have two graphs. One where the initial value is 0 and another initial value is 1. So we'll do 0 and 1. Now, again, since we're given the derivative function, we are given what? Given the slope. So what is the slope of f of 1 and 2? 1. So that means for both 1 and 2, the slope is 1. So at 1, I should get 1, and at 2, I should have 2. So that's why I have a nice little constant function. Now, if I'm starting at 1, I should have an up 1 and up 1 constant function. All right. Now, as we are going from the rest of these values, the slope is changing. Okay. So what is the slope at 3? 0.5. So we should go up from 2 to 3, we should go up by 0.5. Right? And then from 3 to 4, we should also do what? Is it 0.5? Well, let's see this. What is the overall change from 2 to 4? 1. That probably be easy. A little bit 4, my overall change should be less. Right, so we should go up by 1 by each 4. Now, by the time we reach 5, my change is a negative value. I've gone up about, or gone down about a half. Now, because these are not constant rate of change, it'll look more as a quadratic. Peaking at 4. Again, we know we peak at 4 because that's where the derivative is 0. Same thing here. So again, because we have the derivative functions, and if I want the original function, you have to technically integrate. Okay, what we can't count for is whatever constant I have. So they give us two different constants we could. Um, so whatever constants we have, that's our initial starting value. So my area is going to change depending on whatever my constant value is. Okay. So we need to remember. Okay, integrate from a to b of f prime of x dx is equal to the total change in f from a to b. Also remember derivative charts. Right, use English. So as f prime is increasing, that means f is what? If f is increasing, that means f prime is positive. But if f prime is increasing, that means f is
Like exponential.
conjugate. Okay, f prime, in this case, my f prime is constant. Now f prime is constant, it's just a linear function. But then f prime became decreasing, which means it became what? Conjugate, which is what we can see in the graph. Okay. And as we can see, f has a max where f prime changes from positive to negative, which we can see right here. This is a max. So you can try example 2. Okay, start at 0 and then start at 1. Again, you can just do 0 first. What should happen to your function if you start at 1 instead? Each one is again, you want to see what is the overall. You're going to use the area under your derivative curve to find your total change in your function. So, what is the area from 0 to 1? The area right here. Negative 1. So that means the total change from 0 to 1 should go down by 1. Starting at 0, 0, 0 to 1 should decrease by 1. Again, my derivative function is underneath the x-axis, which means my actual function is decreasing. Where my derivative function is above the x-axis, my function is increasing. So again, where derivative is negative, the function is decreasing. Where derivative is positive, the function is decreasing, right? All right. Now, the slope is not a constant slope, so it's going to be perfect. Because this, remember, for derivatives, they always kind of go down by degree. So if you see the derivative is a linear function at this point, that means your function on the lower quadrant in shape. So it will be curved. I'm not going to draw. We could draw the curve. It's fine. But it will be curved. All right. Now, from 1 to 2, that area is also positive 1. So that's where it should get back up to 0 again, curve. Now, at 2, what changes in the derivative?
Become concave. Just the.
It becomes concave down. So this is where concave up, which means at 2 I should have an inflection point on my function. Yeah. So this is where it becomes concave up. And it still increases by 1. So I still have a change of positive 1 here, but it should be concave up in this case. This is concave down. And then we have negative 1 getting back down to 0. Now again, all that's going to happen is if I start at positive 1, is everything shifts up 1. So the idea here is, you remember doing graphs and how we use derivatives to shape our graphs? It's kind of the same concept. We're just kind of doing it backwards than we used to do. Or we have this derivative and we have to go back into the original function. The application of integration was applied by using that concept of area as an overall net change. All right, so figure, example 3, next page, figure 6, 7 is the graph, derivative f prime, the same thing. This time we're starting at 100, starting here. Sketch the graph, do all the critical points, inflection points, given coordinates. Again, right here, we have a net change of, this is 10, this is 20, so 100, right? What happened? 10 times 20 is 100. So it should go up from, now that's from the next 10 points. So from 0 to 10, it should go up by 100. So right here. All right. Now we do know that this should be an inflection point. Right? Where here we are concave up, and here we are concave down. So that should concave up. There's one down. Right. Now we are also still going to have a positive change of 100. So this is still positive 100. So from 0 to 20, we should have another up another 100. So right here at 300. In this case, it is concave down. We have 10 and 5. Actually, we can just do 10 and 10 since that's the way. So that should decrease. It should be a negative 50. But halfway through that, we're going to have another inflection point. Because it changes from concave down to concave up. So at about 25, right, halfway through that, is going to change from concave down back to concave up. How would you find f of x given this graph? Really, it's a tough question. What would you start at? F of x is at least what? 100. You have to start at 100. That's constant value, so 100 plus, since again, this is the derivative function, right? The integral from let's see here, 0 to x of f prime of t dt. So what does this look like?
Which is about
Yeah, this is the second part of the fundamental pyramid calculus. Right. And it doesn't really matter what that bottom constant is. But we can put a 1 because you have this difference. Because it's going to, we take the derivative this way. All right. So here we have a function in BT. So select shows the velocity function of a twice differentiable position function measured with the second are given in the table below. So this is v of t, okay? Estimate the total change in position, which means we need s of t. So we're going to integrate from 0 to 9 of v of t without function. Okay? So here we are starting at 0. Okay, starting at 0. So s, but we'll try to create an st. Okay, so from what's the let's see here. We have v of 0 times the change in here, change here is 2, plus v of 2, and that's value, times the change, which is 1, plus v of 3, times the change here, which is 6. Now, the next thing is we have v of 0, v of 1, v of 2, v of 3, v of 0, v of 2, v of 3. So this is going to be 3 times 2 plus 6 times 1 plus 10 times 6. Gives you 6 plus 6 plus 60, 72 feet. Again, this is an estimate because we're assuming that there was no differentiation of change. There's no alternating change between them. We assume there's a constant rate of change between 0 and 2. Okay. So from 0 to 2, we were going a velocity of 3 feet per second. So overall, for 2 seconds, we had 3 feet per second. That gives us 6 feet. From 2 to 3, we now have a velocity of 6 feet per second. So for 1 second, we went a velocity of 6 feet per second, so 6 feet. And then from 3 to 9, we're going 10 feet per second. So for 6 seconds, we're going 10 feet a second, 10 foot a second, which gives us 60 feet total. So adding all that up gives you 72 feet. Again, we're just assuming that that cost, there's an immediate change in velocity. Okay, that's why we're using approximation, because we don't know everything. You have to basically use approximation when you're going to chart these situations. So now if my initial position was 10 feet, what would my ending position be at 9 seconds? What would we do?
just add.
Yeah, just add 10 plus 72, we give you 82 feet. All right. The Pearson velocity function is increasing. If it actually is, what do we know about our estimate from part B? So v of t is increasing as an increasing function. Your derivative is increasing. All right. what kind of function do we have, or what is the shape of our function if our derivative is increasing? Concave up, which means our estimate is what? It's concave up. Our estimate is what? Underestimate. So if VT is increasing, then this would be an underestimate of the actual area. So the position at T of 9 is likely greater than 82 feet. So if V of T is increasing, our function concave up, our estimate is likely underestimate. Making actual value that says from part B, not from part A. So we're assuming we start with 10 feet in the position. So actual value at T equals 9 greater than 2 feet. Is there a moment on the time interval from 2 to 3 such that the velocity is 9.3 per second? Why or why not? Yes. So VT is continuous since the total position is differential. Okay, so it didn't say it's in fact twice differential, so it is continuous. And V of 2 is equal to 6, V of 3 is equal to 10, and it's 9.3 between 6 and 10. So yes, according to the IVT, it is possible. And I've lost it. So, 1, V of T is continuous. Since it is given as differential, which we need for the IVT to apply. 2, V of T, or V of 6, or V of 2 is 6. And V of 3 is 10. Therefore, well, that's 6 is less than 9.3, which is less than 10. And the IVT applies. Should exist. Let's see if it could exist. OT that VT equals 9.3. Won't. The point of going through all this is to know when we do what we're going to do tomorrow and Wednesday, how to justify our answer. And how to write, how to justify it. Yes.
Why doesn't it say that there does exist? Why does it say there could exist?
Oh, yeah. Yes. Your issues, but it does exist. All right. So similar question. Let that be continuous function. His graph is shown above. Let h equal the integral from -2 to x of f of t. So basically, we're treating f as the derivative function of h. So so if h is the integral of this function, that means h is what? Geometrically, h is what? The area. Okay. So where is the area equal to 0 on the interval from -2 to x? Okay. I can see where you should get 1, but you might miss the easy way. What does an integral always equal 0?
So these, as
When the bounds are the same. Yeah, it's the easy one. You'll not think about it because it's just we never use it really. But basically, h of x is equal to 0 at the interval from -2 to 2 of f t dt. Or -2 to -2, sorry. Okay. But where else is it equal to 0? So basically, when the area cancels out, where does the area cancel out? -2 to 8. -8. So also integral from -2 to 8 of f of t dt, because this gives me an area of, right here, this is 1, 2, there's 6, and this 4.5. Right? So this is an area of 4.5, -4.5, and -6. So also so h is equal to 0 at t equals -2 and 8. What is h of 0? What's the area from -2 to 0? 6. What is h prime of 0? H prime of 0 would be the rate of change between 3. Yeah, 0 to 6. So it's a constant rate of change, which is what? 3. Okay. Again, you can just kind of think of it as slope. We went from 6 minus 0 over 0 minus a -2 was our actual values. So that gave me 6 over 2, which is 3. Right, or you can just average the area. All right, so what is H? So I have H prime of 0. Another way to think of it is H prime of x is equal to f of x. So H prime of 0 is equal to f of 0. And that's again from that fundamental theorem of calculus. If we took the derivative of this, we would just get f of x. On what interval is h increasing? Show the analysis that leads to conclusion. Where is h increasing is where the function is what? Positive. So I recognize h is increasing from, now again, looking at this graph, we don't have to go from, actually, you kind of have to go from -2. So from -2 to 3. Since h prime is equal to f, which is greater than 0. What is the maximum value of h? What is the maximum value? What is the minimum value of h? Justify your answers. Now, to justify the answers, we actually do have to find the values. So where do we think the max value of h is? 3. So, let's see here. We can find the max value of h prime of x is equal to 0, which we found that to be 3, which is f of x equals 0 at x equals 3. So, again, the test is what values do we plug in when we're testing for maximum value? The endpoints. Okay, so my endpoints here are on the graph. I'm just going to actually use the endpoints on the graph. We can even use the actually one negative 3, 3, and 9. So we have x and h. Right? Now, let's look at this. What is h at negative 3? Remember, h is the integral from negative 2 to x f of t dt. If I'm going the integral from negative 2 to negative 3 of t dt, what do I do? Negative. Yeah, negative integral from negative 3 to negative 2 of t. What's the area from negative 3 to 2? 3. So my answer is negative 3. All right. So what's the area from 0 to, or negative 2 to 3? 10.5. And what's the area at 9? Negative 3. Well, so, therefore, yeah, max value. And these two would be my min values. For what interval is h concave down explained? 0 to 6. Yeah. Because 0 to 6 person decreasing. Yeah. H is concave down from 0 to 6. All right. As h prime equals f is decreasing on that. That is it for next. So homework is on the AP website. It's area accumulation functions. Tomorrow we will do. Oh, Yeah. So tomorrow we will start these. If we finish this tomorrow, great. We may not finish this tomorrow. It may take 2 days, which is fine. But yeah, we start again, just reviewing. Some of this is going to be review of what we did last semester. Okay, so our notes are going to start having some just extra practice questions as we get closer to the AP exam. So, we will have a day which we do practice the AP exam because it is online. Okay, I don't know how the whole process is going to go, whether the entire thing is online or if it's like basically the AP website to where even the pre-response questions can be typed in. I hope not, because it's difficult. I mean, how much experience do you guys have with that? No. Yeah.